Hi, hello, this is Srija. I am from CSDC section department. Today I am here to say about few information about soil corrosion. Now, this slide going to be say about an introduction to soil corrosion. This slide is telling about just like any other environment, soils can be corrosive. In corrosion engineering, this becomes an issue because a wide variety of the structures that people and industry rely on are buried under the ground, such as vessels, storage tanks, and pipelines. Although soil corrosion can lead to financial losses and structure failure, there are measures that can be implemented throughout the design and production process to prevent it. In order to do this, it is important to develop a fundamental understanding of the potential of soil to develop corrosion. We go into next slide. Now, this slide is about what is soil corrosion. Soil corrosion refers to a very complex phenomena that involves several variables. This may include chemical reactions with certain elements that occur in solids. For instance, variables in soil characteristics and properties can have a huge impact on the corrosion activity that occurs in buried structures. Now, this slide is saying to be, for instance, carbon steel's response to corrosion in soil basically depends on the soil's nature and other factors in the environment, such as oxygen and moisture. Such factors are capable of producing intense effects in terms of corrosion rate and severity of attack. In a worst case scenario, a buried vessel may perforate within a year. So, what are the key factors in soil corrosion? We discuss about it. Okay. In general, the following will dictate how corrosive soil will be. Soil will corrode in these levels: high electrical conductivity, high levels of moisture, high levels of dissolved salts, and acidity. There are many other factors to consider when it comes to soil corrosion, and these should be examined very carefully to prevent extreme attacks. Now, we'll discuss about some problems of the soil corrosion. The soil corrosion problem. The damage of corrosion could result in billions of dollars in expenditures. The most significant portion of losses related to corrosion involves the corrosion of metal or steel structures that are buried in soils. Metals that are in contact with materials such as soil can develop a corrosion potential. In most instances, the rate of corrosion can be so fast and the severity can be so extreme that it results in structure failure. Thus, the mechanism of soil corrosion should be known along with the strategies that should be implemented to avoid or to mitigate the corrosion of metal when it comes in contact with soil. Essentially, there are basic issues that are significant to soil corrosion. These are as follows. Soil corrosivity can be associated with the aeration level, salt content, water retention, and acidity of soil, as well as the existence of ionic species in the soil. Galvanic processes that occur when metals come in contact with soils. The mitigation strategies that are being used in the practice of modern engineering. The use of sacrificial anodes to provide protection. We go into next slide. So In this slide, we are going to discuss about aeration. So let's dive a little deeper into these basic factors. Now, aeration. Aeration is described as the amount of air trapped in soil. This is a very essential factor when it comes to corrosion, as it also affects evaporation and water retention rates. Soil that is well aerated is less prone to corrosion because it has higher rates of evaporation and lower water retention. The gradation and the size of the soil particles also play a vital role in determining the degree of aeration. For instance, sandy soils are more favorable as these have bigger particles that permit faster evaporation and better aeration. After water is introduced to the soil, a fast way to categorize soils according to their aeration is by looking at the color. The colors are yellow, brown, and reddish soils have good aeration, while the gray ones are considered unfavorable. Now, let's come into this resistivity and moisture content. Soil corrosivity is largely dependent on the moisture content of soils compared to any other variables. Water is considered one of the major elements needed for the process of electrochemical corrosion, along with other components such as metal and oxygen. Essentially, corrosion will not take place when the soil is totally dry. According to various studies, higher moisture content can reduce the soil resistivity, which can in turn increase the potential for corrosion. Bear in mind that when the soil has reached its saturation point, extra moisture will have little or no effect on the resistivity. Now, let's come into this slide. This slide is about acidity or pH. Soils possess varying levels of acidity, ranging from a pH of between 2.5 and 10, 2.5 to 10. When the pH level reaches 5 or below, fast corrosion rates as well as early pitting in steel or metallic structures are likely to occur. A pH of 7 or neutral is favorable because it can minimize the possibility of damage due to corrosion. Take note that soil's intrinsic pH can be affected by other factors such as rainfall. Now, let's come into another redox potential. Redox or oxidation reduction potential refers to the activity or strength of oxidizers and reducers in relation to their concentration. Oxidizers accept electrons while reducers lose electrons. A high redox potential trend tends to signify high oxygen O2 concentration level, low electron activity and oxidizing conditions, while a low O2 concentration means low reduction potential and high electron activity and reducing conditions. I hope you understand about this particular slide. Now let's get into another slide. Now, how to control soil corrosion? Soil corrosion affects almost all structures on Earth. As such, the right measures should be implemented by industries, especially design engineers, in order to avoid or at least prevent the damage that corrosion can cause. Basically, there are key ways to control soil corrosion. So we have three ways. We see the three ways now. The first way is cathodic protection. Cathodic protection is a corrosion control technique that is typically used to manage the corrosion of metal by transforming it into the cathode with an electrochemical reaction or cell. For further reading, we have to go into deeper of cathodic protection and anode backfills. Now, we are entering into our next way, it is sacrificial anodes. The use of galvanic anodes is one of the most effective ways of protecting various steel structures from the harmful effects of corrosion. A good example is zinc anodes, which are highly capable of providing galvanic protection to metals that are in contact with soils. Now we just enter into our next slide. Now, the third way is the use of protecting coatings. The use of protective coatings on metal structures buried under or in contact with the soil can significantly prevent the occurrence of soil corrosion, depending on the level of protection. Generally, the soil corrosion can take place in almost all structures that are exposed to soil. Even so, accurate design, favorable production environments, and adequate protection levels can prevent the harmful damage that can be brought about by corrosion in soil. Now we are going to another slide. So this is a slide. It is discussing about issues relevant to soil corrosion. There are 6 factors that affect the corrosion of metals in contact with soils. The relative corrosivity of soils can be described as a function of level of aeration, water retention, dissolved salt content, soil resistivity, acidity, and presence of ionic species. Now, the third point is the process of galvanic action when metals are in contact with soils. The two primary soil corrosion mitigation strategies used in modern engineering practice. Two metals are most common to sacrificial anodes in a soil corrosion. Now, we look into another slide. Now, these are the factors affecting the corrosion process. The factors are, there are 6 factors that are affecting the corrosion. They are, first is aeration, as we discussed about aeration. Second one, water retention. And third, dissolved salt content, soil resistivity, soil acidity, presence of ionic species. So these are the 6 factors that are affecting the corrosion process. In this slide, we are going to discuss about soil tests. Soil tests are very much important to these soil corrosion and effects. Soil corrosion does not lend itself readily to direct study in the laboratory. However, indirect methods involving the action of differential aeration cells have yielded valuable information in comparing the probable corrosivities of different soils towards steel. The details of this technique were described by Densham 136, Ewing 137, Fedger 138 140 to 141 and by Logan et al. 142. And these are some scientists. The Fedger 138 to 141 polarization break. This period is called polarization break, and the polarization resistance methods have been studied by Jones and Lowe in relation to their effectiveness in evaluating corrosion rates of buried metals. A Holar bridge circuit was used to remove IR contributions during the measurement of the polarized potential. Jones and Lowe, on the basis of their studies of buried steel and aluminum specimens, concluded that our polarization resistance of most useful and that the polarization break had the serious limitation difficult to identify the breaks in the curve. These two scientists uh, did experiment on polarization resistant. The due period of 138 to 141 called polarization break. The next slide. Now, soil corrosion is a complex phenomenon with a multitude of variables involved. Chemical reactions involving almost each of the existing elements are known to take place in soils, many of which are not yet fully understood. The relative importance of variables changes for different materials, making a universal guide to corrosion impossible. Variations in soil properties and characteristics across three dimensions can have a major impact on corrosion of buried structures. Now we have a formula, that is Z is equals to A into T to the power of M. Now where the Z is called either the weight of loss of maximum pit depth, T is called as time of exposure, and A and M, they are constants that depend on the specific soil corrosion situation. The response of carbon steel to soil corrosion depends primarily on the nature of the soil and certain other environmental factors such as the availability to moisture and oxygen. These factors can lead to extreme variations in the rate of the attack. For example, under the worst conditions, a buried vessel may perforate in less than 1 year. Although archaeological digs in arid desert regions have uncovered iron tools that are hundreds of years old, some general rules can be formulated. Soils with high moisture content, high electrical conductivity, high acidity, and high dissolved salts will be most corrosive. The effect of erosion on soils is somewhat different from the effect of aeration in water because poorly aerated conditions in water can lead to accelerated attack by sulfate reducing anaerobic bacteria. The effect of low levels of alloying additions on the soil corrosion of carbon steels is modest. Some data seems to show a small benefit of 1% of copper and 2.5% of neon plain carbon steel. The weight loss and maximum pit depth in soil corrosion can be represented by an equation of the form. So this is a picture of the soil corrosion. Let's get into another slide. The influence of soil's chemical properties is reported as a root cause of failures of buried pipes. The chemical constituents of soil react with the surface of unprotected buried pipes, which in turn results in the corrosion of pipes. However, there is still no complete preventive solution to the corrosion caused by the chemical constituents of soil, even in the presence of advanced corrosion protection techniques. As per above referred studies, soil constituents cause corrosion of buried pipes. These include moisture, contents, pH, temperature, soil resistivity, soil type, soil particle size, permeability, differential aeration, and sulfate reducing bacteria. Researchers have adopted various approaches based on field testing and experiments to investigate these factors. Soil has been imported as a main stimulant causing failure of buried metallic pipes. So this is a pie chart or bar graph we can think about this. The yellow line indicates corrosive soil. It is the 4 percentage, and the green is indicate to others, and the red indicates coatings damages or degradation, and this yellow 67 percentage it is belongs to stray currents, and the 12 percentage is belongs to dissimilar metal or soil environment. With this, I'll end this session. I hope you understand everything. Thank you.